Last talk of the day, last hour of the day, I guess, hour and a half. Start time of 4:20, always a good way to start. Did anyone see Super Troopers 2, by the way, that came out on 4:20? It's pretty good. I live in San Francisco, so it's legal. Actually, I can't smoke the California weed. It's like way too strong. Way in fact, I was speaking in San Jose recently, and someone came up and said that they work for a dispensary lab, like a marijuana lab or something. And he was all weird about where he worked until the session was over, and then he came up and said, "Yeah, we're actually using TensorFlow and things to test the weed, the THC and the CBD and all that stuff." I was like, "That's awesome." Yeah, they're in Oakland somewhere. Okay, so the title's kind of crazy. We're going to cover a lot of ground. I have 260 slides. This is normally an 8-hour talk. And I'm also speaking at a meetup right after this over at DataZoo XU. How do you say that? Is it DataZoo? I should probably learn that before they host me. So I'm going to do probably an even longer version tonight, if you guys are in the mood for it. Let's see. We're going to cover some Jupyter stuff. We're going to cover CUDA. We're going to cover GPUs. We're going to cover TPUs. Who came here? Oh, yeah, actually TPU is not even on the thing, so in the title. But yeah, you guys are going to get the latest, greatest TPU action. I just got 400 from Google. I was trying to spin them up, and there's a little bit of an issue. So I have screenshots, though, which is, I guess, the next best thing. So let's see. Yeah, we'll be doing Python. So who here uses Kubernetes, just to kind of get a little survey? Who here uses Docker, I guess? I'll probably start with that. Okay. Who here uses Spark? All right. TensorFlow? Like in production TensorFlow? Yeah, TensorFlow is kind of fun. So let me think how we're going to do. I probably won't get to the Kubernetes stuff. That's at the end of the talk, but I'm going to reference it. I'm also going to tell quite a bit of stories about the Bay Area, where I moved from Chicago about 8 or 9 years ago. It's always good coming back here. Yeah, who is that? All right, and then Trevor there. Okay. Trevor, raise your hand. That lives in Chicago. Yeah, so great town. I love coming here. This is not recorded, so I'm just going to say this frankly, but the girls here are way more attractive to me than the girls in San Francisco. There's something about, so I'm from the Midwest, so take that however you want to, but people in California don't really catch my eye until I come here. So that'll be one sort of introductory inappropriate thing that I'm going to say. I'll probably offend quite a few of you. But this is East Coast, so I could do this. If I was West Coast, see, this is like my outlet to all of the pent up. I don't know. I should just stop right there. Also, too, Dunkin' Donuts. There's no Dunkin' Donuts in California. I think there's one in San Diego or something totally random. So I've been drinking nonstop Dunkin' Donuts. So that's why I'm able to stay awake at 4:30 here. Which is 1:30 California time, so I don't know why that would be an issue. So yeah, learn a little bit about you. I'm going to say a few things about me, and then we're going to get right into it. And who here uses GPUs on a day-to-day basis? If you didn't have GPUs, you'd be in trouble. All right, so you in the front second row here are going to be, you're going to like this talk. You can raise your hand for all this stuff. All right, so tonight we're partnering with the local Spark Meetup. I spoke there, I think, last year. It was over at Echo Nest, which is now Spotify. We had a great time, packed, full room, tons of questions. It was all about Spark. Yes, I run this thing called the Advanced Spark TensorFlow Meetup. And it started off the Advanced Spark Meetup. I used to work for Databricks and got kind of, I saw Databricks going through that marketing phase where a lot of their meetups and conferences were marketing materials, and this drove me crazy because I'd be working the booth at Databricks, and I would get so many technical questions, and people are like, yeah, what's going on with Databricks? Why are you guys just talking about marketing stuff? So I created this Advanced Spark meetup really on the sly, like Databricks. Yes, I'm going to tell a lot of fun Databricks stories too. Does anyone here work for Databricks? Does anyone here work for Google? Any, what's the other big one that I make fun of? Yeah, no, Kafka I like. Yeah, that's mostly oh, yeah, Amazon. Yeah, does anyone work for Amazon? Do you? Okay. Oh, yeah. Okay, sweet. Yeah, there goes half my material. So we'll be talking about SageMaker today. We'll be talking about Google's cloud. Yes, they have an ML engine that's kind of similar to SageMaker. It kind of predates SageMaker, but actually in like yes, like most ways, I think SageMaker actually has the advantage, and I'll explain why here in a sec. But yeah, just going to get through slide 4 here out of 260. So there's a whole ton of material. This is only an hour and a half or whatever. There's a whole ton of material out on YouTube if you search for this meetup. And there's, I think the closest is a New York chapter actually. So we had a meetup a few days ago that I still haven't uploaded the video, but it's basically going to be similar to this talk. So it's going to have a lot of TPU stuff. Tons of slides. It's about a 3-year-old meetup, and we have 15 or so chapters around the world. So heading to Budapest tomorrow, or Sunday. Yeah, so here's the meetup tonight. The address is there, 281 Summer. It says 200 people are going, so I think that's the maximum RSVPs, but right, like you guys know meetups, you can just show up, and half those people won't even show up. So if you haven't signed up already, it'd be cool. So a bit about you guys. I'm assuming that this is what you're kind of interested in. And if not, you should probably leave now because that's what we're going to talk about. But things like hyperparameter tuning, right? These are terms that are typically used for offline, right? When you're trying to find the right parameters for your model, the depths of your trees, and all the normal stuff that you read about and use on a day-to-day basis. So, but there's also hyperparameters like beyond training. There's actually hyperparameters for the optimization step post-training. And so yeah, we're going to highlight that. And then there's kind of a third set of hyperparameters, which is at serving time, right? Like when this model is actually in production, there's actual knobs you can turn there, which is really cool. And so we'll talk quite a bit. And what's really cool is that TensorFlow, this is why we tend to focus on TensorFlow at my company Pipeline, is there's so many things you can do post-training that nobody, people have never even seen these optimizations because R doesn't have them, scikit-learn doesn't have these post-training optimizations, ways to fuse together layers. And if you're familiar with Spark, there's something called Project Tungsten, especially the second generation, Spark 2.0, where you can actually fuse together maps and filters, and there's huge, huge optimizations that can happen. And so the same stuff pops up with a, production first sort of framework for AI, which is what TensorFlow is that. Right, so these other ones like MATLAB and R and that kind of stuff, they didn't really ever want to leave the lab, right? These things were meant for sort of batch processing and batch recommendations or batch machine learning that would then go into a database and then get served. And so they didn't really have any runtimes that could perform for real-time AI. And so that's where TensorFlow comes in, right? And there's something called MXNet, also by the Amazon guys, pretty much. There's a standard that the Microsoft and the Amazon folks have created. It's called ONNX, ONNX, and it's basically like PMML, except it's 30 years later or whatever. But it's a standard that you can convert your cafe model and CNTK, which is the Microsoft framework, or MXNet, into this common sort of PMML-like framework, right? The prediction model markup language. I can't remember. And then you can then build a consistent runtime to actually serve those models, but you can train them differently. So sort of interestingly enough, TensorFlow does not support that standard. There's really not much plan for it either, from Google. Yeah, so they already have their own runtime, and they actually have quite a bit of optimizations called XLA, right, the Accelerated Linear Algebra, that kind of works with their runtime and lets other hardware people build to this XLA kind of intermediate representation. So yeah, and then the other thing is just being able to like deploy these models quickly, right? This is something we got used to at like Netflix, where we were always pushing out microservices and new models and experimenting at the speed of thought. And since Netflix, I kind of thought, this was almost, what, 7, 8 years ago now, 6 years ago? The world hasn't really changed, right? Like data science world has not gone this direction, right? Which is unfortunate. There's kind of this, big divide between production engineering and data science and like machine learning, and so that's what like Pipeline's trying to do, is to fuse these together. Yeah, so being able to actually push these models out, to like push them out safely, meaning to shadow mode them, right? So you could push out a new version. You can actually change the runtime, so you could switch over to like an Onyx runtime, or just switch back to Python, or try out like TensorFlow serving, or try out the Nvidia runtime that's optimized for GPUs. And it's that same model, but actually different runtimes. And so you can push these things out. If they tip over because of some bug in that specific runtime or whatnot, you just tear it down, and it hasn't affected anybody because it was in a shadow mode the whole time. And so the ability now to track models in production, right, and having insight. So again, this is something Netflix took for granted. And I feel like data scientists kind of hand their model over and then they lose insight, right? And it's just data. And like data scientists like data. So the more data we can give you guys, the better. And so the ability to make changes offline and see their like performance, the characteristics. Did I actually push out a model that's now 500 layers deep that had 99% accuracy offline, but now it takes like 35 seconds to score, for one prediction, something like that. So just kind of giving more knobs to turn, and then that like feedback loop between online and then offline is very important. And yeah, the ability to like shift traffic and do A/B tests and multi-arm bandits, and like detect that like predictions are now cheaper over on Google because you just lost a bunch of Amazon spot instances, and so now the price for like Amazon servers has gone up, so we could actually slowly shift traffic over. So yeah, and like this is all like open source stuff. Yeah, that's obviously we have to please the investors. We have to build, one of those weird like enterprise tools and all that stuff. Which, yeah, I've been in Node.js hell for the last few weeks. Yeah. And then of course all this GDPR stuff, right? So traceability. So with Pipeline, right, like we can't actually explain, right, those predictions that are coming from the neural networks. That's still, right, like a bit of a theoretical situation there. There's a few companies tackling it. There's this project called Skater. I think it's my buddy down in LA, actually. Yes, I didn't put that together. It's like SKATR or something weird. His project does just this. He works for datascience.com, but it's kind of his little side project. So he's trying to tackle this. What we're saying here is that we could actually trace the prediction and show you which models participated. Right? And so like that gets you a little bit closer. Yeah, so key takeaways, I pretty much already said these. The big one is that you can actually generate, right, like hardware-specific optimizations, and this is both offline and for online. And so we'll talk about some of the Nvidia GPU, right, like optimized runtimes here in a bit, and some of the things that like TensorFlow can do as well. Who here would love to do continuous model training? That's kind of the holy grail, right? And so do you guys know about partial fit? It's the scikit library partial_fit. Yeah, not a lot of people know about that. They kind of snuck it in, yes, Andreas Mueller or whatever, just kind of slipped it in there. And it's like the most, yeah, right, like to me, it's the most exciting part of right, like scikit. And so these neural networks actually want to continue to be trained, right? That's why you're typically dealing with something called a checkpoint file, which is kind of weird, right? You're like, why am I dealing with this checkpoint file? Isn't it done training? And yeah, so these neural networks, they're like grad students, right? They just never want to leave the lab. They just want to stay there and not, actually get out. Yeah, was that like offensive part number 2, yeah, like part 2 there. And so we're trying to bring these things out and yes, make them deal with the real world. So this continuous training, this is actually sort of natively supported by these neural networks, right? And so you can just keep pumping. So that checkpoint file becomes like a frozen asset that then gets pushed out to production. But there's still kind of the researcher part of that network that is not frozen that can continue to be trained, and that network stays intact. And so, yeah, like we'll talk about some of that stuff here as well too. I'll actually show you guys what a model looks like after training, and it's 92 nodes. And then when you go to actually prepare it, it'll go down to 5 nodes or whatever it is, just for like linear regression, small little network like that. So Pipeline is open source. We actually just hit, I think, 2,600 stars a couple days ago. It's pretty bad when you always know the number of this at your project. Yeah, my skater buddy was like, yeah, I just hit 493 or something. One funny thing here is that we actually started talking to some of these VCs, and this is a little Bay Area comedy here. And at the time we had hit 2,000 stars, and the person says, a very, very prominent VC, like one of the older ones, actually said, well, to us, that's worth $3 million in seed funding. And so we quickly started all these campaigns to get our GitHub stars up. Yes, at the time they were worth 1,500 apiece. He said the next step up was 6,000 stars, I think, and that was 10 million. And yeah, I don't know too many projects that have 6,000 stars. But yeah, and that's Ehrlich there with his, yes, I know how to meet ladies, HTML. Yeah, that's the shirt. This is East Coast, right? I'm still on the East Coast? Okay. If you want to see QuickStart, you can go QuickStart Pipeline. Who here has used Kubernetes through Docker on their Mac or their Dell or whatever? Yeah, it's awesome, isn't it? It's like game-changing. So yeah, I don't really talk about this much anymore because it's been so long, but like one of the reasons I actually created Pipeline was that Docker was now being supported on people's local laptops. And so this is huge because you could actually train a model. That's what we do with this QuickStart. Train the model, slurp that model into Docker, and then burn it in as a Docker image. And now that exact same model with the Scikit version that you want, with the TensorFlow version, all this stuff, is now that unit, right, that's being moved around from environment to environment. Thanks, Gene. And so you don't really have to worry about these dependency issues between dev and prod and your local laptop. That's the actual asset, is this sort of executable model, right? You're kind of hydrating it, is a term I use. And yeah, so once, because I didn't ever think Docker was going to be supported on Mac. Like I thought it would probably get supported on Windows because maybe Microsoft would do something. But and then just a few months ago, they started supporting Kubernetes. And this is huge because Docker actually has their own called Docker Swarm. They were always a little bit weird about Kubernetes. In fact, one of the first Docker cons I went to, they actually didn't have Google there at all, like as a sponsor, which was weird. They had Amazon and they had all the other players. And someone actually called out the CEO of Docker and said, hey, we don't even see Google on like any of these signs. What's going on? Is it that bad? And so yeah, just about 6 months ago or so, there was KubeCon. Was it Copenhagen? Or no, or not KubeCon, it was DockerCon, where they finally announced that Kubernetes as a first-class citizen. So now Kubernetes runs locally on the laptop. And so this opens up whole clusters. Now, like you don't really have that much RAM. You might have 8 or 16 something. You can't really get a huge cluster, but you could start to do the same sort of internal DNS and things like that is being done. And so you're not hacking ports and all that stuff that could slip out and then cause problems in production. And so this is something, again, at like Netflix, we had this immutable architecture. And this is the #1 thing that like data science teams say to me is, well, I have this Docker image, that's cool, but how do I get the model in there? And I'm like, no, there's a step before it, you burn it in. And they're like, no, but that doesn't work in our environment. And we kind of go back and forth, and we're actually kind of lifting that like firm thing. So yeah, like to be totally transparent, it's not something that teams really want because they don't want this kind of heavyweight sort of like burning the image and then like deploying it. That's our preference because we're always thinking about production, but they're kind of just doing, fast things on their laptop and that kind of thing. So we're trying to find the right balance, but sort of ideally, you would start tracking that like Docker image around, and you could tag it with the git commit hash, for example, that you use to actually commit the model, and then everything can be tied back to each other. So let's see. Yeah. Oh yeah, there's a community edition right there, by the way. So it's totally free. There's GPU. We get tons of miners. Yeah, Bitcoin miners. Yes, I'm always amazed when they start up a process on that machine because it's called like mining or like Bitcoin or BC or something. And it's like, can't you at least obscure it so that I have to, search a little bit to find this? What's causing 99% of the GPU to be utilized? Yeah, and then that's a standard slide for the VCs. I assume some of you have probably heard of Michelangelo, right? Like Uber's Michelangelo. Yeah, a few hands. So this paper is awesome, and it basically kind of describes like pipeline, right, which is really cool. So with Uber, they have this internal sort of AI platform, they call it. It's called Michelangelo, and it can pretty much do everything from the data ingest to training models to doing the evaluation of a model to like deploying models. So yeah, from 4, 5, and 6, that's all kind of after training. We sort of blend the validation, like step number 3, with the rest of it. So we're kind of 2.5 and down because we actually validate models in production, right? Which is very interesting. This is not done, right, like pretty much at all. And this Michelangelo thing actually doesn't really do the evaluation online. They just do it offline. You choose the model and then you deploy it and then deal with those consequences if it dies. And so, yeah, I've actually been talking to the Uber folks. We've been collaborating on this stuff. It's pretty cool. There's also something called FB Learner, but again, this is more on the training side, right? So this is hyperparameter optimization. And this other paper was actually 2014. I had gone back and started looking at patents, because that's a big deal in the Bay Area. And I was searching, model predictions and model experimentation and blah, blah, blah. And like Google has like 5 million patents around this stuff. And they're from 2007 or something ridiculous. So they've been thinking about like machine learning in production for way, way before we were. Is that me? Oh my God. It's actually off now. Yeah, I don't know. All right. So there's this paper, it's called The Machine Learning High Interest Credit Card of Tech Debt. And the summary here is that there's so much going on with machine learning infrastructure, right? That there's, it's a huge distraction, right? And so that's why they've spent quite a bit of time, building out these like huge clusters and that kind of thing. Bottom right, yes, interestingly enough, is a job posting by my old company, Netflix. And someone sent it to me and said, hey, they're like describing pipeline here, right? Like, why don't you, talk to these guys? I'm like, yeah, so I know who that is. Actually, my old boss from Netflix, she left, she like did a couple shitty startups and then came back to Netflix. And now she's, so she is that role, right? Because I actually just went to like update it and see if it was still available. And I searched for that title and then, her name came up. And there's this other, and so it's describing the ability to like push out models quickly and sort of iterate. Right? So companies are starting to think about this stuff, which is cool. And it's more than just TensorFlow, of course. I'm going to kind of skip through. This slide was actually 3 bullet points before I got on the plane. And I got kind of bored. So the highlight here is in the upper right. We just registered noflaskapp.com, and that kind of summarizes. If you are like productionizing your machine learning right now, you're probably spinning up a Flask app. And Flask is fine, right? Like we use Flask, that's fine. It's this, we use Flask for sort of admin and stuff. Like we're not actually putting it on the like real-time path. But it's more this false sense that this model is now in production and it's production ready, right? There's more to it than just spinning it up behind a web port. Right, like a web server and then serving predictions. And people do everything from calling scikit-learn predict directly to kind of building their own in Python. You know, some people are getting fancy and calling C, and yeah, there's a lot of weird stuff going on. And so, yeah, basically, if someone next to you is talking about Flask and they don't really have a story about, well, how do I monitor this thing, right? So this is more than just monitoring like, right, like DevOps monitoring. This is actually monitoring how is the prediction doing relative to newer models that are being deployed. And the ability to sort of label data, you know, did this campaign actually work, right? 48 hours later, 2 weeks later, whatever it is, and then start to, you know, tear down these poor performing models, and just basically always being in a state of experimentation. Right? So the other fun term here, there's this term train to serve, and this actually comes from a Google paper on TensorFlow, one of the more recent ones, where you're like training to actually serve this model, not just for the sake of training. There's training serving skew. There's a few different terms for this, but the concept is clear. This model is 99% accurate offline, and it's, you know, 60% when it's actually being exposed to the real world. There's some things here about turning knobs and that kind of stuff. We're going to get into all that. This was from a couple weeks ago, so I think I've like hammered home the point here, which is model inference is kind of where people are looking. And actually, I was surprised. I was at this conference just a couple months ago, and part of the keynote was, right, that the Nvidia Corporation has this thing called TensorRT, which we've been using for the last year, but they're really doubling down on this thing. And it's more than just those Jetson and kind of small device things. This, you know, this is actually data center type predictions as well. So they're in fact, during the keynote, they actually had a Kubernetes cluster, and they were showing model experimentation going on. So they've been thinking about this quite a bit. Yeah, and there's tons more here, right? There's like energy efficiency, there's throughput, yeah, all that stuff matters here. This is just another way of saying it, but the bottom right like really shows what's going on. There's millions of these predictions happening per second, and there's maybe, you know, right, like 100 jobs happening per day. And so, and there's huge amounts of like these optimizations that are just not yet explored on the actual prediction side. And of course, offline, people have been studying these hyperparameters for years and years. So there's like quite a bit of performance being left on the table and cost savings and that kind of stuff. Right now, Bay Area is not in a cost savings mode, as you can all imagine. You know, there's, yeah, obviously the peaks and the valleys. And so all of my advisors say, don't talk about cost. No one, yeah, like these VCs don't care about cost right now. So, which is funny because that's how it was at Netflix as well too. When I showed up, I'm like, oh, I can have a dev cluster that's as big as production. All right, let's do it. Yeah, like 5,000 nodes, and yeah, we'd always be hitting the Amazon limit and stuff. So here's kind of these three phases, and there's, you know, training, of course. There's this new phase that we're trying to like promote and like raise awareness. It's, you know, kind of auto-generating new models, right? And you could take a model, you can shrink it down, you can quantize it down to half precision, because you don't need full 32-bit precision, let's say. And so from like one model, we could actually generate, you know, 5 or 6 variants and then put them out into production. And there's this concept here that I kind of jokingly have a trademark on. Yeah, I don't really have a trademark. It's the efficiency score. And it's kind of weird because it's like, well, the prediction, the cost per prediction is lower for that first line, which has a GPU, so that's kind of weird. And then the second line, you know, which is scikit-learn, has a very, very high efficiency, but its cost is higher. And so here's what's going on here. This is actually purposefully set up this way. That training job cost a lot of money offline, right? We were using GPUs, we were, you know, and it's not shown there kind of per you know, piece of training data or something like that. Maybe we should add that, but it was very expensive. And so right when that model first goes to production, it's not very efficient. And not until the model actually starts to run and run and run. And now we're starting that, like, efficiency is dynamic. It's not fixed. It's going to go up over time. Whereas the scikit one was super cheap. You know, it took 80 seconds versus 270 seconds, for example. You know, maybe it's running in a cheaper data center. You have to kind of figure out the cost there. You know, it's the like stereotypical White Plains data center. I feel like there's a lot of data centers probably in White Plains, right? It's very humid. And And so maybe Amazon's like a little bit more expensive, but yeah, these things are always changing. And so that like prediction accuracy is very interesting too. So how do you label or like talk about sort of AUC and this like accuracy with like data that's not being labeled, right? So this is unlabeled data coming through, but really after there's an objective there with these models, which is did they convert? Did they? And so maybe there's a Spark job running in the background that's going to be updating this thing, saying, yeah, this actually is, it did well offline, but then also online, it's like holding up pretty well. This is just a bad copy and paste where it's the same value. All right, I'll skip through this, but so this is a way to actually track all the hyperparameters and then the results. And so of course, right, like we have PipelineDB, we call it, where we're storing all this data. And it's different things. So at training time, there's actually more than just the model parameters, right? So we're trying to like raise awareness here. There's things like the network speed, and this changes from like cloud to cloud, from cloud instance to like cloud instance. Actually, if you're using GPUs as well too, there's a cost from the CPU to the GPU. Some of these GPUs are actually network attached and not on the physical board, and that's really significant. That like makes or breaks these like performance benchmarks people are always doing. There's something else here too, which is the Python distribution, right? Yeah, so Intel actually has a really, really good Python distribution. No one talks about it. They don't, for some reason, talk about it. But it's actually, it has MKL, which is kind of their like, it's kind of like a GPU library, I guess, but it's CPU. It's like BLAS, right? Like the basic linear algebra subroutines. It's very, very optimized for like linear algebra, for these kind of things. And so it's built in, and just switching from like the Anaconda Python to like the Intel Python actually makes a difference in some cases. So this is something, this is a hyperparameter that you're playing with, and you're going to have to feel out your data set and like your environment. There's things like with Amazon, there's these things called placement groups, which puts nodes closer together. And I know these really well from, at like Databricks, we actually did this. When we would spin up these clusters on behalf of our customers, we actually made sure there's this little checkbox that like really no one knows about. You would say, yeah, I want this entire cluster to spin up inside of one placement group. And that's significant because that tells Amazon, yeah, you're going to pay a little bit more, but these nodes are all on the same rack, or as close together as possible. So there's a lot more hyperparameters here, more at the system level than people think about like traditionally. So there's the hyperparameters, and there's the actual observation. So that's training time, and then there's optimizing. This is like post-training optimization. So this is that like weight quantization going down from 32-bit that we trained at down to 8-bit. When you drop precision, by the way, and this is not statistical precision necessarily, but it's the number of bits that are used to represent a float that you're trying to learn during this actual model process, this model training. And so typically what you would want to do is train at higher precision, 16-bit, 32-bit, but then when you go to actually run the predictions, when you freeze that model and then push it out to production, you would lower the precision, and that's going to make the math a lot faster, right? Because you can multiply 2 8-bits much, much faster than you can 2 32 bits. And it's pretty much linear because these like modern like CPUs and GPUs can actually pipeline together. So if you have a 32-bit like GPU core, for example, so you can actually put 2 16 bits in there, right? Like you're not doing it like yourself, the actual compiler's doing it, but you get like an instant 2x speed up. And so, yeah, we'll cover that here in a bit. And then at like prediction time also, yeah, there's those different runtimes. There's this thing called batch size window. So when you're making, high throughput predictions, you're like batching up a bunch of requests, building up a big matrix. Yeah, there's a bunch of zeros, maybe it becomes a sparse matrix at that point. But you're moving all of that over. And so this is many requests coming from all across the world that happen to end up on one single process or one single GPU. You build up the big GPU, pass it, make one big calculation. Because of the properties of linear algebra, we can actually take it back after it's been calculated, split it up, and send it back to the columns around the world. So yeah, that's one of those sort of aha moments when you're like, oh yeah, that's why I sat in that stupid linear algebra class for a while. All right, so here's the SageMaker Google Cloud ML engine. SageMaker was released in November at the now famous reInvent conference, which I had to stop going to because I didn't make it to any sessions. I would just be hungover for 5 days. So now I just stay at home and watch, the live stream and stuff because I'm safe in my own home. But if I'm out with friends, probably Trevor knows this. I'm not good when I'm with friends. I can't control myself. So this is a fairly new service, and it supports when it first dropped. So like SageMaker is kind of like the old Amazon ML service that they had that didn't really go anywhere. It has its own Amazon models, right? But then there's one little thing, there's one little drop down, because I didn't really pay attention when I first heard about this service, probably about 2 or 3 months before it was actually released. I was kind of trying to figure out where Amazon was actually going to go with this. There's one drop down that says, oh, by the way, we'll take just a random Docker image. And yeah, it's going to run inside of our containers, and you can't egress out and start to spam, email spamming and that kind of stuff. It's a contained environment. But that's now the gateway. So these pipeline runtimes, right? These optimized different things we can try and experiment now can get uploaded. And so we support SageMaker, of course, right? It was literally changing an Nginx path that they need that Docker image to be listening on, and I think it was port 8080 instead of 80 or something like that. So so literally just change one thing, and then our Docker images work within it, which was awesome. And they support a little bit of the A/B testing, where you can split traffic and that kind of stuff. Similar to how Amazon Web Services rolls, they give you the building blocks, and then it's kind of up to you to actually stitch them together and create the value. So, and then there's Google Cloud. So this is an interesting thing, and I shouldn't really bash these guys too much because they've done a lot for the community and everything, but this service blows. It's so bad. And it's gotten better. One downside, it can only operate at the model level. So there's no drop down for a Docker image. And then whereas SageMaker supports GPUs and can has all the CUDA drivers already built for you and all this stuff, it's great. With Google Cloud ML, it's all right, just send us your trained TensorFlow model, right? Of course, yes, it can handle training as well too. And then we'll just put it on this crappy CPU cluster that we've had for years. And this is very interesting too because the pricing model for these things is quite different. So with SageMaker, I think it's about a 40% markup on the EC2 cost, and you can choose the instance type that you're using for both training and for serving. Whereas with Google Cloud ML, it's a flat 30 cents per hour on top of, and so I was trying to figure out this pricing. I'm like, yeah, how can it be so different? And then I realized that you have no options during serving with Google. It's literally send us just the TensorFlow model, and then we'll put it on our cluster. So that was really interesting. Oh yeah, Riley, the other thing about SageMaker, to Amazon's credit, they actually have a ton of examples, and it's all the latest TensorFlow. And right when SageMaker came out, they had figured out all the weird things with distributed TensorFlow and had an easy way to overcome them. They kind of had their own config file, which I was always a little, sort of weary of, but it's very similar to the open source one and actually works. Whereas with Google, I was just trying to get these TPUs spun up today, and there were obvious things that aren't working. Yes, Azure ML, the big joke here is I lost my Hotmail password a bunch of years ago, so I haven't quite gotten in there. The funny thing about Azure ML, to be fully transparent, is that probably 60% of our customers are on Azure, and it's a lot of the oil and gas and a lot of these banks and things like that. And so it would seem, if you looked at our profile of users and customers, that actually Azure is the most popular. But yeah, of course, there's a whole ton of Amazon as well too. But all right, I'm going to skip through this. Here's that TensorRT thing, and some benchmarks. So this is it's the Nvidia. They actually can take your TensorFlow model or your Caffe model, and they can kind of post-compile it or post-optimize it, post-training optimize it, and get it down. They'll do all these GPU tricks that only people from Nvidia know with low-level CUDA, and they could do all kinds of crazy stuff. And they're claiming 41x speed ups in certain cases. And But now keep in mind that these benchmarks are also with the latest GPU, which is the Volta V100, which has these things called tensor cores that are very similar to the TPUs, which I'll show you here in a sec. TensorFlow Light is interesting. They've been very careful recently about trying to not force people's brain to go to mobile phones and to iOS when you see this word TensorFlow Light. Like this used to be called TensorFlow Mobile, I think, at one point, or I think there still is a TensorFlow Mobile, but it's more TensorFlow Light. And what's happening here is you can actually, and there's like tons of examples for like iOS and Android and all that, but you can take like your model and pass it through this TensorFlow Light post-training optimizer step. It will actually like see your graph, you tell it like where to start for the inputs, where the output is, right? There's this big neural network. And this post-processing thing, I think here they changed it, it's like Taco or Toco or something, will actually pretend, you know, that it's starting from scratch with like no operating system, nothing. It'll only pull in what's specifically needed from both the operating system and TensorFlow runtime and kind of stuff it into a little, you know, bag or whatever, like a little Halloween thing. I'm picturing my nephew with the little pumpkin. And then at the end of that, he's going to dump out the pumpkin and build a C library. So there's this, and so it's an optimized, it's the bare minimum to get you from the start of that network to that actual prediction. And then that is, you know, and so this is where models go from 70 meg, right, like potential runtime footprint, down to like 70K. And so this is the, you know, huge difference in being able to actually deploy on these, you know, tiny sensors. Not, you know, cell phones, we have 70 meg, that's fine. But yeah, so there's a lot of like production thinking and small device stuff. So let's shift a bit. We're going to kind of talk a little bit about GPUs and TPUs. There's this kind of big like race going on between Amazon and Google in terms of GPUs, and then of course, like we all know about these TPUs, right? Tensor processing units, which we're going to tear apart here in the next couple slides. So yeah, DOSBO hourly rate $650 seems crazy, right? It seems like the first days of the cloud. So this is for a TPU with these specs, and the other thing to point out, so there's a couple key differences with these Google Cloud TPUs. So before I was talking about Amazon with their GPUs, and you have to get one instance type with Amazon that has a GPU. I think there's something called the Elastic GPUs, but I've never actually gotten that screen to work. When I try to click, I always get routed to like the docs or something. But you, and so for these TPUs, you can actually like spin up a cheap CPU and then start to attach TPUs. And actually throughout the training job, you could scale up and scale down. And this is huge because with GPUs, you probably have to provision it up front. If you're not using that GPU, you're still paying for it. Here, you could just, and you know, if the training job for like whatever reason starts to get backed up, you just add a bunch more TPUs. And these things all federate, right? These TPUs, yeah, so unlike GPUs, these TPUs kind of, they're like little kids on the playground. And they kind of swarm together and they get bigger, and there's a lot of value and a lot of comedy coming out of that swarm. With these GPUs, they're kind of like standalone, you know, bullies, like off to the side waiting to, I don't know, punch these kids or something. And so right, like the more TPUs that you add, these things come together in what's called pods. And yeah, that's an example. I think that was the one that was used to train AlphaGo or AlphaZero, or yeah, one of those, in like record time. And there's actually this new benchmark that I think just came out this week. It's called the Dawn Bench or something, out of the Dawn Lab from Stanford. And yeah, these TPUs blew, yeah, just like, I think it trained something in like 30 minutes, and the next closest was like 2.5 hours or something like that. So yeah, very interesting benchmarks and some awesome compute power. Okay, so this is where I start to bash Google for a bit. And I saw this with Databricks, because Databricks was always doing these little shenanigans, trying to bleed between open source. And when you clearly own, you know, the open source project, and then, oh yeah, let's just slip in like a, you know, something that's super critical. Oh yeah, we got in trouble from the Apache Foundation, things like that. So they were always kind of dancing that line. And so one thing to keep in mind, people don't really think about this much anymore, is that TensorFlow is not bound by the Apache project. So this is a very, very important distinction between Spark, which to me was kind of one of the last Apache bastions or whatever, like going that route. And so Google didn't really need it. Yeah, they already have 800 million GitHub stars times 1,500. That's a lot of potential VC money. So this is a screenshot of this open source tool that comes with TensorFlow. It's called TensorBoard. And it's showing you your graph, and it's basically always done this, since the super early days of TensorFlow. And it's kind of fun and visual and cool. And suddenly, I think it was TensorBoard 1.6, there was this TPU compatibility button that showed up. And so this is like, hey, yeah, we could actually run all of 92% of this graph, and yeah, we'll back up to CPU or to GPU because we don't fully support your graph, but you can get like 92%, and they haven't gone as far as actually putting a dollar amount, like we could save you, $5,000 on this job or something, but you can kind of see that, potentially happening. But they're sort of inserting, because yes, I didn't mention it, Google TPUs you can only get with Google Cloud. So basically, if you do get kind of hooked on this, you're going to have to use Google Cloud, and then that helps out Google. So yeah, tiny bit of evilness. I just hit this today, actually. And I had someone else working on the TPU, so I didn't actually experience this myself when we were putting these slides together. But I was trying to get this working today, and I was like, oh, that's what he was talking about. I was trying to access my local, so you spin up a CPU, you then attach a TPU, and it's all done through HTTP, or actually it's gRPC. So it's not physically part, but it's close to that CPU, so it's still network attached. But yeah, this is a subtle thing. If you want to use TPUs, all of your data has to be in Google Cloud Storage. So that's kind of interesting. That was the actual error, and when I Googled it, it was actually on the TPU page. It's like, oh yeah, I was like, yes, we don't even support local file system. Because I pulled down a bunch of data onto that CPU machine in the cloud, ran it, and I was getting this error. So I was going to have to move it to a Google bucket. I just thought the other guy working on it just like Google Cloud Storage. So that's another little evil thing. This is where it starts getting cool. So these TPUs, there's this profiler. Actually, the slide's a bit flipped here. There's this new profile tab that shows up when you're using TPUs. And at first glance, I was kind of like, oh yeah, here we go. It's going to tell me how much utilization and all that stuff. And then I started poking around, and I'm like, wait a minute. If I back up a slide, it's actually talking about that input pipeline as well, right? So it's telling you that you should be doing prefetch, which in this case it was. It's showing you how many threads are being dedicated to pulling from Google Cloud Storage in parallel. So it's not just profiling the actual device, the accelerator. It's actually looking at the entire pipeline. And this is a best practice of TensorFlow, is to put as much into TensorFlow as possible, right? And it's because they can do all these little optimizations. It's kind of the same thing as the Spark people telling you, don't use any UDFs, because UDFs, we don't know what to do with those. So you can't fuse them together and all that. But this is taking it one step further. So one thing Spark was never really good at was profiling. They kind of had a crappy tool, and there's been a lot of people trying to build tools, and there's always pushback with the Spark project because they didn't want to expose those metrics because they could potentially change the internals, and so people are always hacking and making things public and that kind of stuff. But here, they're front and center saying, we want all of your stuff in here. We'll actually show you how that there's unused threads that could be used to actually pull in parallel. There's like unused cores on the CPU as well. And so the way that you get this is you have to install, it's a pip install. It would be useless if you don't have a TPU, so you can install it all day on your Mac. But it's pointing, and then it's called capture TPU profile. And once you start that up and it points to the tensor board, the same log directory where all of these events are going, right, during your actual TensorFlow training job, they all end up here in TensorBoard. You can kind of see everything together, which is really nice. So here it's showing which operations were taking up the most time. Down in the bottom, you can't really see it, but in red it's saying that you are not bound by I/O. that it's actually the accelerator's problem. And that's kind of a good place to be, actually. In like most cases, it's the opposite. These accelerators sit there, these GPUs sit there idle. It's because you're not really pulling in parallel, or you have a slow network, or HDFS is backed up, or whatnot. So here they're saying use Google Cloud Storage with these TPUs, and that will be the best guarantee, the fastest. I'm going to skip through this. This is basically QuickStart. This is building the Docker image locally, going through the different steps. That's interesting. So here's that post-training. So the step 1 and 2 were about training. Here, so that's what like linear regression looks like after it's been trained in TensorFlow, and it's 92, 94 nodes, something like that. That's the graduate student, and that has all the backprop and everything. It's like waiting to be trained more. When we actually go to push it out, we're going to do something called freezing. There's a couple different ways to do it now. There's actually this new model format within TensorFlow called the saved model format, which is always confusing. But it will basically take that big gobbledygook, strip out all the training things, all of the TensorBoard logging nodes, right? Because this is just a graph. It's a directed acyclic graph, just like Spark, but it's more on the numerical processing and less on the data processing. That like dataset API, so there's a dataset API within TensorFlow now that kind of bleeds into Spark's sort of ETL territory, which has now caused the Databricks folks to focus more on like AI and that kind of stuff. So it's like Spark is trying to become more AI, and TensorFlow is trying to go the other way and trying to be more sort of data processing kind of earlier in the pipeline. And I think they have a pretty good shot, especially because of those profilers, right? Because that was something Spark never had and still really doesn't have. So yeah, this is like taking that model, shrinking it down. That bottom part is the that like model runtime could be 70 meg, because if you have to load the entire TensorFlow like runtime, I think that's 50 meg or something like that. With this TensorFlow Light, you have just the little like Halloween basket, and that's it. And that's the final result, is like whatever fits inside of that. Okay, it's more on the pipeline stuff. Oh yeah, this is building 3 different Docker images, the exact same model. So model path, which is the bottom parameter in each of those, but we're changing the runtime. So we have TensorFlow serving CPU, TensorFlow serving GPU, and then TensorRT, which is that one by the Nvidia folks. And right, so again, it's the exact same model, but we're actually auto-generating 3 different versions, and then you can test and push those into production. Here, you're actually running that Docker image locally on your laptop, and then running a load test. And so some of you might be thinking, well, it's not really a real load test because it's on my laptop, right? Yes, I agree, but you ran that same load test with the previous model, and you on the same machine, and you will on the next model. And that kind of gives you an early indication of if I've completely destroyed like performance on the prediction side, or so that like you don't even have to make it out to dev and to prod and staging and get laughed at by your peers. You can just kind of laugh at yourself locally and then go back. But like this happens all the time, where people push out these 500 layer deep models, and yeah, it's great offline, but that like 24 milliseconds there shoots up to 24 seconds and that kind of thing. Here's some of the model splitting and shadowing features there. It's just this open source command line, parameters that you pass in for the different variants. So we're making experiments here with different splits, and then tracking all this stuff. And so now we could actually make recommendations, right? That's kind of that's the like commercial side of pipeline, right? Is that we are going to be collecting this data, and then we can start to make recommendations for this particular model type. We can actually say, use this kind of EC2 instance, this kind of network, use the White Plains data center, that kind of thing. Yeah.
Why that you're showing, is that proprietary, or is that also part of open source?
It's kind of mixed. Like the bottom right is open source. The top right is the proprietary one. Yeah, I know. Trust me, man, I'm a community guy. It drives me nuts. But I have to pay the bills, I guess. I don't know. Yeah, what do people always say? You can get very, very far. So one of like if I'm talking to you guys, I'll say, yeah, you can pretty much do everything. If I'm talking to the VC, I'm like, oh, we're holding this out. But like between like me and like, you guys, you can do pretty much everything. Now you're certainly going to have to maintain your own database, maintain your own Kafka cluster, maintain all this, and that's the value add, right? Is some of like the operational stuff. And what's interesting is that we're actually not like a managed service. We actually deploy inside of your VPC. It's like the exact same deployment as Databricks, where the sort of management part of it runs inside of our cloud, and then we VPC peer into your cloud and spin up the model servers and that kind of thing. Yeah, all the data stays in, and that's just because we're like lazy and don't want to get all those certifications. Yeah, this is actually comparing. So this is actually this cool demo where we like simulated losing those spot instances and then shifted traffic over. And so we're tracking price per prediction. Yes, all that stuff is in the open source. And then you would then start to detect and then shift it over. Okay. Oh yeah, this is like multi-arm bandit stuff kicking in. So one thing, I'm sure you guys are at a data science conference, so you totally know this, but these A/B tests, as we traditionally talk about, are fixed, and they could be 2 weeks, and they're basically not optimal for the end user for the duration of that experiment. This is why you end up in a crappy Netflix like recommendation stage for a couple weeks. This happened to me recently with Uber. I was trying to call an Uber X, the cheaper one, and I literally could not swipe over to get to the X. It was only showing me premium and black or whatever it was. And the person standing next to me, I was like, hey, yeah, can you try this? And they were like, yeah, I can see X. And like literally, it was like 2 weeks on the dot that I was stuck in this crappy test cell. And then I just didn't use it for 2 weeks. And then, but these multi-arm bandits will like detect that my regular pattern is I do 3 to 4 per week, per day. Yeah, those are big hills in San Francisco. And then they would either pull me out of it, or they would end the experiment, or like something would happen. Right? These multi-arm bandits are much more dynamic, and they can only do so much that the statistics let them do. But the sort of flagship case is it'll like detect an early winner if there's 3 experiments and C is doing really well. It'll just start slamming C. It's kind of like when you're like talking to a girl and you're like, oh yeah, I'm going to keep calling her a lot, and that's going to help. And then she stops answering, and then you're like, oh, okay, yeah, now I get it. So, yeah, that's a real life story. So you would then shift the traffic and kind of spread it out again evenly. So you would sort of send traffic early, and the best case is that early winner continues to hold up with this new traffic. The worst case is it doesn't, and now you then have to spread it out and then try again. So, also with these multi-arm bandits, you can early terminate, right? And so, which is basically like pulling people out of that experiment. And like with the traditional A/B tests, that's not statistically possible. If you do, you basically lose the power of the test. With these, for these bandits, you could actually sort of drain them of their prediction value, or sorry, their like statistical, what's it called? Like there's some threshold that like down below 5%, right? Like now we can early terminate because we're not learning anything more at that point. Okay. Here's some of the profiling. So this actually got moved into TensorBoard. This like used to be kind of a side thing that Google Chrome, combination of Google Chrome and stuff, but you can actually see where time is being spent on these GPUs. You have to do a little bit of instrumentation for your TensorFlow code in the upper left, but then these metrics start to show up and you can see. And this chart I'm going to show here in a sec next to some of the like XLA stuff, the accelerated linear algebra, where it fuses together a bunch of those things. All right. This is kind of cool too. So we actually built this. And so we're talking sort of conceptually here, right? If you have, like whenever you make predictions, so backing up a slide, this is kind of real-time prediction analysis. This is all open source. You see the input, you then see the actual like, confidence values. This is classic MNIST, it's the digit 2. You see for the 3 different models, how did they predict, right? And there's a clear winner here. 2 is the case. They're slightly different, but in like all cases, 2 is the result. The worst case scenario is that you have 10 options and the confidence comes back 0.1, 0.1, 0.1 for all 10. And so we can actually detect this and pull these aside. And then later on, or like throughout the day, we're actually posting these to Slack. And of course, you can dial it down so you're not getting blasted. And then you can have this like human in the loop. So actually, one user of ours has like an internal like data science team of about 60 people. And so all day they're just on there, like whenever they get bored, they just go and they relabel. Now they're not labeling MNIST, right? They're labeling fraud. It's similar to Airbnb type company where there's user-generated content, and there's always people trying to work around these systems, fraud-wise, putting in their phone number. And if it's not a confidence prediction, maybe it was 40% fraud and 60% not fraud, it'll get sent over, and then and so now this becomes labeled data and gets put back into the training cycle for the next run. So yeah, that was really cool. It actually came out of us building this, sort of real-time analysis, and then someone was like, wait a minute, yeah, we could actually, since we're getting these confidence values, we could actually highlight them and push them out, or like correct them, and they chose Slack. Yeah, Slack's pretty cool. You can do a lot of fun stuff in there. It's kind of addictive. Chaos Monkey, anyone heard of this? Famous Chaos Monkey, yeah. So we use something called Istio. It sits on top of Kubernetes. We're working with the Mesos folks to get it working there as well. So this is where you could actually start to inject faults and simulate certain instances being down, prediction servers being down, right? And like the big joke at like Netflix is that all of us employees were like basically part of Chaos Monkey. We get fired for crazy reasons no one even knew. Yeah, so pretty much every couple weeks there'd be someone on your team that the manager had to form around. All right, yeah, this major player is gone. We have to rebuild the team. We have to do this. So it was kind of like a human Chaos Monkey. I don't think the HR people would really appreciate that, but that was the best we could surmise because we're like, this guy was actually really good. Yeah, so there's ways to actually stick in faults and make sure that the cluster is working around, and this is all configuration-based. This is actually part of Istio and something called Envoy, which is by the Lyft people. It's a C++ routing thing that Istio builds on. Continuous model training, I think we all pretty much know that, or at least have familiar with TensorFlow with GPUs. My suggestion is get your model working on a CPU first, and then spend the nights and weekends and like breaking up with spouses and that kind of thing, because it's going to be a long weekend. So this is actually inverted from the way I would like normally describe it. I just copied this from somewhere else. But there's the Nvidia hardware is actually on top. There's about 6 layers between the actual GPU and what you're using on, inside of Python. And the reason I point this out is there's been some new hardware advancements that I'm going to talk about the next slide that have gone into the hardware, but the drivers haven't kept up, or CUDA hasn't kept up, or CUDNN. They're about 6 months behind, things like that. And so you might hear something about 16-bit support and try to use it within TensorFlow, and it's just not working. And it's not that you're crazy, it's that literally it takes a bit for the NVIDIA folks, from the left hand to the right hand, from those hardware folks to the software folks. Okay, so here's that new Volta V100. It's actually about 1.5 years old, but it's still in its sort of 2-year hardware cycle. So 53,000 cores, these are 32-bit cores. That's kind of an impressive number, way more than CPUs. These are really, really lightweight, for super lightweight threads. But this is the first time that we saw these tensor cores. And these are optimized for a particular operation, which is matrix A times matrix B plus vector C, something like that, right? Which is very common in these like deep learning workloads. And so also they're 16-bit native, which is very important. And what's the other thing about these? You have to have like your matrices when you're doing a matrix multiply, right, these have to be or not powers of 8, they have to be multiples of 8. And this is like one of those weird hardware things that you'll like tend to find out if you start to ask around or start to do the empirical testing. Like, there's always magic numbers with these hardware devices, and it's kind of not really made public, but like TPUs have them. We're still trying to explore those. They're not very obvious, but these tensor cores kick in, and this is where when you go from 32-bit down to 16-bit, I think yeah, this one. So this is the same matrix multiply at, so this is 32-bit, and that top row is Volta V100, so right below the full precision and half precision. That's the new V100. This is the Amazon instance, P3 instance. When those tensor cores kick in, now it's 4 times the throughput, which is really powerful. The thing is that we didn't see this at first. Like, we had heard, but like we didn't know where that number was, and then we sort of empirically figured out it was if you have your matrices dimensions or that are multiples of 8. And the way that you, as a coder or as a data scientist, gets it that way, you really have to start to pay attention to the size of your input-output channels, all the like convolution things, and so this is kind of annoying. You shouldn't have to do this, right? In some cases, right, so the Nvidia layers, the software layers, those drivers and CUDA and all that is actually padding, and that's the best case scenario, because now it's still faster to pad and hop onto that sort of like multiple of 8 than to be on a multiple of 7 or 5 or something like that. Let's see. Yeah, so this slide is actually showing the 2x speed up when you have 2 floating point 16s going into a floating point 32 GPU core. So that's pretty intuitive. Okay, yes, I understand I can pipeline and put those two together. Some benchmarks. This is where you start seeing the cost per the cost per image and that kind of thing. So yeah, these are some of the early numbers. There was one that just came out recently. Again, it's called Dawn. I think it's called Dawn Bench. That is very focused on the dollar amount. So I think the TPUs were like $45 to train this huge data set in like 45 minutes or something. The next one was like $150, and it took twice as long and that kind of stuff. So a bit of history about half precision or the 16-bit stuff. This is kind of cool. This actually stems from some like early work back in the late 90s by Silicon Graphics. The first commercial request was by the Industrial Light and Magic folks, people like Lucas, right? They were kind of the first ones back in 2002 that were doing a lot of image rendering and a lot of super detailed, and they were just blowing the bank on memory and disk, and so they were kind of begging for. So yeah, they're up in Skywalker Ranch or whatever, maybe 30 minutes north of San Francisco, and they were like, hey, yeah, we're here in the valley. Can somebody provide us hardware that will give us good, right? It's kind of like compression, I guess you would kind of sort of naively think about it, but it's actually this other term here. It's this dynamic range, and this is kind of a mathematical term, but essentially the sort of intuition is that the larger precision, the more bits that you're allocating to a float, the more dynamic range you can pick up. Okay? And if you go down to int 8, for example, that's actually really bad because you only have between like minus 128 and plus 127. And it gets, at like floating point 32, it's a huge range, pretty much unlimited. There's one little trick where empirically, if you actually truncate by like floating point 32, just kind of lop it off and don't actually quantize it, that can actually like preserve this like dynamic range better than floating point 16. It's not IEEE standard for like whatever that's worth. Right? Yes, I was seeking an IEEE joke a few weeks ago, and someone was like, "Yeah, there's a joke, but there's like an RFP that's been sitting for a while or something." It was some IEEE joke like about slow-moving process. So, all right, what else here? This is how you would actually turn it on within TensorFlow. So like I was saying, there's about 6 layers deep to actually turn this on. When you use TensorFlow on a TPU, all of these have been set. They've pre-compiled TensorFlow for the actual TPU. You're not getting just a stock like open source version. These TPUs again are 16-bit native. The GPUs below show the first time was the Pascal P100 that they actually supported 16-bit. And then again with these Volta V100 Tensor cores are even better. There's actually, I think, 2 or 3 more flags that you have to turn on. It's kind of like each release with Spark when there's like 500 more configs, right? Like config entries, and you just kind of hope that that those defaults work. And then they like deprecate them because they just want to experiment and then they pull it out. A bit more on the like reduced precision, just because I think this is interesting. So why don't we go down to 4-bit or 2-bit or even 1-bit neural networks? And like this is actually really interesting. So the sort of intuition here is the deeper you can go, you can actually like lower that precision but still maintain like good sort of overall accuracy. So these neural networks really like sort of individual and then coming together, right? Similar to how I was describing those TPUs, it's more that actual network and those connections that matter. One other subtle thing about when you drop down to smaller precision, so yes, the math actually becomes faster, but there's a caching aspect to this too, right? So something that's 1 bit can actually stay closer to the actual ALU, to the arithmetic unit, or the logic unit, and isn't getting flushed to DRAM and back up and that kind of thing. Yeah, there's obviously like less energy, less bandwidth needed across the network, or like between these devices, less memory used, and there's a whole ton of benefits. So yeah, this is kind of the, yeah, my buddy texted this to me. He was explaining the linear algebra and how this works. Yeah, this is a couple of years ago, but I kept it in here because it's funny. When you have those things, so yeah, this is actually padding to get to those multiples of 8. It's not a multiple of 8, but just kind of bear with me on the like texting image. A couple other optimizations. Does anyone know about Numba? Yeah, Numba is kind of, if you think of it as a drop-in replacement for NumPy, and it's by the Anaconda guys who very into scientific computing, of course. Pretty much kind of started it all there. And they've already written, so right, like one thing about Python that took me years and years to understand, I always kind of rejected Python. I would always just like label it as slow and the GIL and all that. But when you're talking about scientific Python, right, like that code is actually, there's C versions, right? And it's basically like getting through Python as quickly as possible and going to the C version. So think of that same concept, but now going to a GPU, a compiled version. So these GPU kernels have been built by the Anaconda guys, by the community, and by just swapping it in, it'll find the GPU, hopefully. That's not usually that easy, but and start to actually do these calculations on the GPU. TensorFlow JS, this is probably my favorite. This was announced at the Dev Summit. And what's cool is, so this is TensorFlow in JavaScript on your phone in a browser. So if you're sitting here not doing anything with your phone, you could be training, right? This is, what was the old screensaver thing that was out of like NASA or something, right? Where when you were kind of sitting idle, it was always, you could opt into this sort of decentralized. Yeah. So that's kind of what I think here. It's and I've heard people talk about TensorFlow JS in the context of sort of decentralized, privacy-friendly, right? So all this GDPR stuff. If you think of a federated training job that each device doesn't know about like the other device, and it's just getting bits of data, and that small amount of data is not enough, right? There's some hand waving going on there, but that small amount of data is not enough to identify, and it like has to be brought together somewhere, and like think of so yeah, that's the context I've seen this brought up in, is these devices that are each seeing part of it, and of course the flagship. Yeah, this is Mr. Pac-Man, by the way, not Miss Pac-Man, which I was kind of bothered by because I like Miss Pac-Man better. All right, I'm going to skip through some of the more advanced TensorFlow optimization stuff. Let's see. Oh yeah, have you guys ever heard stochastic, yeah, it's called stochastic graduate descent? Because it's like the original days. Yeah, my buddy said that the other day, I was cracking up. And then simply go down, right, like SGD, because you're always going down, so you can find the minima. Fun way to kind of remember it. So this is now bridging TensorFlow or Spark to TensorFlow. So there's a couple ecosystem projects that you can add into your Spark job, and at the end of it, actually create what's called TF record, which is TensorFlow's kind of parquet type thing. So yeah, some of this stuff, it seems like Google themselves don't really care about, but if you talk to a Google like developer advocate or a Google solution architect, they're spending a lot of time here because everybody has Spark, and they're like, oh yeah, let's start to work on this project. But if you were just talking to the TensorFlow team, they probably don't even know this exists. Speaking of Spark, it now supports Kubernetes, kind of cool. Couple options for TensorFlow on Spark. Probably the project I've heard the most success is TensorFlow on Spark by Yahoo. And they've done a bunch of optimizations. They've like integrated RDMA and like the InfiniBands, and basically got rid of gRPC and whatever Google was pushing because their network actually works better with these other protocols. So they actually contributed that back. It's basically using Spark as the distribution mechanism, and then treating TensorFlow as just like Scikit or some library that's on each of the workers. But it's doing, it's a bit more complicated than that, of course, but that's basically what TensorFlow on Spark is. And that was kind of early. There was this TensorFrames project that came out of Databricks. It really hasn't been touched that much. Then the Spark Summit's coming up, and it's now renamed Spark and AI Summit. And it's actually the first Spark Summit that I would probably pay money for because I haven't gone the last few years because it's just a bunch of boring Spark stuff, or it's Spark stuff that I'm already familiar with, I guess I should say. But there's a whole lot of like AI at this new conference. And so, yeah, this was one of their sort of early things, take data frame and combine it with TensorFlows. Let's see, let me get to some good stuff here. Oh, this is how you can, so as of TensorFlow 1.7, I believe, you could actually talk to Kafka and treat it like any other data set, or rather data source. So this is kind of cool. This opens up the path for the continuous training. I'm going to skip through all this. It's more. Oh, so more on this data set. So this is, again, where TensorFlow is becoming more like Spark. There's this data set API. It works really well with Python generators, and yeah, you can very easily create these iterators, one-shot iterator, which is one pass through, or these reinitializable iterators that will go through once, shuffle, and then go through again, which is, yeah, these neural networks, if you're not doing time series, you don't want the network to learn the pattern in which that data was introduced to that network, which is why you always want to shuffle. And so this is like significant because if you have a bunch of files that happen to be ordered, like alphabetically or by some like numbering system that has nothing to do with the data, that network will pick up these patterns. And so you want to create a little bit of randomness. This is data set dude, I call him. He's never responded to me ever through LinkedIn or Twitter or anything. He's he's a pretty big, so that like tutorial right there is the entire data set, like API. It's in a Google sheet or whatever. Yeah, there's a lot of good stuff in there. I have some good. Here's more on TPUs. So I kind of glossed over the estimator API, but if you are starting anything now with TensorFlow, you have to be using the estimator API. And I point this out. Actually, I'll just talk about the estimator API because it's so significant. Okay, so the estimator API, this is a way to write your TensorFlow job so that it'll work on your laptop and on a cluster. Up till the estimator API, that transition, this is what we spent a lot of early time on. in the like sort of first days of Pipeline was like converting people's single node code that they pulled down from an example into multi-node or multiple, right, like scaling horizontally. And the estimator API, this is one of those things that you could tell came from Google Cloud ML engine. So them trying to productionize and open up TensorFlow and their clusters to the public, because they needed a way, this is Google and TensorFlow, like needed a way for us, like common people, to write our TensorFlow so that it could very easily be distributed. Okay. This part I don't think is evil. This is stuff I would see Databricks do all the time, where they would take a bunch of customer input about Spark, and then they would focus on that for like the open source. Of course, there's always those big customers where you're like, all right, it's not really the most important thing, but let's look at it. So yeah, it's basically this like callback mechanism. It's a way where each node is now responsible. Like there's this sort of like retrieval function for, and so each node then can call that same function and grab its portion of the training data in parallel. Some more details there. Does anyone here use Keras? Oh, how do you say it?
Keras.
Keras. Wow. Yeah, I just said it. So yeah, you can't say it that way. Yeah, people say that word weird. Actually, Gene would ask me how to say Kubernetes before. Right? And I was like, how else would you say it? But yeah, I guess there's a lot of different ways to say that word. So there's a straightforward way to go from Keras to Estimator, which is nice. So Keras is kind of a higher level API that the sort of original intent was to be an abstraction layer. You could plug in different frameworks. Google went and actually hired the guy that created it, and so now all the innovation is happening on the TensorFlow side. Is that even? I don't know. Yeah, I don't use the other ones. I just use TensorFlow, so for me, I don't care. There's these canned estimators. Now, this is a very interesting statistic here. So that, like upper right, as of August, so a little bit less than a year ago, they did a huge search on their sort of internal like TensorFlow repositories. So all the teams within Google, Google Play, Google Store, and all those different places, YouTube, huge fans of TensorFlow. Like the Play Next feature is all TensorFlow. They scanned it, and so like there's this concept of a canned estimator and then sort of a freeform estimator. So canned estimator is pre-tuned. There's subclasses of the estimator API that are in the like physical open source project itself. And I think it was 52% were using canned estimators. And no, it was 58% were using canned estimators, and 42% are using their sort of own, their own custom estimators. So yeah, this is very important because you know that they've tested these things, they've like flushed out these bugs. It's these cool ones like DNN classifier, Tensor Forest estimator. Yeah, these are all canned estimators. So yeah, this is where things get a little bit wonky too. So these TPUs actually have their own estimator. And it's a subclass, of course, of the base estimator, but these TPUs operate a little differently, right? They're like children that like to come together, and there's a lot of clustering and sharding, and they're doing the like leader election for you. All you do is point to one of the TPUs, and they kind of all sort of self-organize and like do their thing. Whereas if you're using GPUs or even CPUs with like distributed TensorFlow, there's no way to like do the leader election without running your own zookeeper and all that. And what was always interesting to me, because like that like Google doesn't do anything single node; it's all multi-node. And they never really offered a way to do really good distributed TensorFlow. And then this comes out, and I'm like, oh, that's why, because they're making it really easy to do it on the TPUs. And not, with fixed resources, you can only focus on so much stuff. With 8 billion employees or whatever they have. But yeah, so you actually take the normal estimator, you would then like wrap it, and same with the optimizer. So that's gradient descent optimizer. You would then wrap it in this TPU-specific optimizer, and then theoretically everything should be handled. yes, that's the same as earlier. This is another view of the profiler. Oh, and so the thing to show here is that this profiler is telling you now, and so this is back to TPU. This isn't the multiple of 8 thing necessarily, but these TPUs have magic numbers. And so here they're actually saying, okay, for like this particular operation, it was an exact fit. It was right, like the exact padding that we were looking for. There's no padding needed. And then bottom right, they're like, okay, yeah, we had a pad from 64 to 128. Yeah, like we took care of that for you, but just keep an eye on it. Maybe change the size of your, like the application layer, right, the actual convolutions and that kind of thing that we're responsible for. There's changes we could potentially make. And so this is where like a lot of their like performance folks are spending time, is actually doing this to tell you how to use these TPUs better. This is like a cool concept. So this is called multi-headed inference. And this is taking data, these features, these like inputs, passing them through the network, and then getting a prediction, actually getting 2 predictions. And so why would you want 2 predictions? Well, you want this, so think beyond just one single network. This is one pattern that was coming up a lot at the recent TensorFlow Dev Summit. And there's been a lot of code going into TensorFlow, into TensorFlow serving, which is a separate project but meant to serve these models, that is hinting a lot at these ensembles, right? And so, so these ensembles are like the ability to actually compose models, smaller submodels into larger predictions, right? Or like larger models making broader predictions is very important. And there's like 2 reasons why that's important. There's, these things could be coming from different teams. For example, if you're a driverless kind of scenario and you're taking input from temperature and from like visibility, and there's like many like different inputs that are saying whether or not you should jerk it to the left or jerk it to the right. Right? That's kind of like a human grokable way to describe it. The other benefit is from an explainability standpoint. The more like fine-grained you can isolate, this particular prediction was because of this data, because of this model, versus trying to jam all of this data and all these different rules into one model, right? So from an explainability standpoint, it's nice to have kind of composable, because it at least gets you a little bit closer. And so this like multi-headed thing, it's actually passing it through one of these like submodels, you can call them. It's making its own prediction and saying, I think you should jerk left because of what I'm seeing and because of the way I've been trained. But here's the final numerical layer of my neural network. So I made a human prediction, which is go left. But now I'm actually giving you that like final layer that's a numeric layer that you can then pass into a subsequent model. Right? So think of it like a feature engineering step. It's taking features that have come in, it's making a prediction, and then converting those features into something that can then be used as input to the model. Okay. So this is one of the things that we do with Pipeline, where think of like Zipkin, which is actually what we use, where we could show all the models that are participating across Python, Java, all the different runtimes, and then show kind of a final what actually fed into that prediction. I want to mention dropout. May or may not be familiar with this. This is a way to kind of shoot nodes in the head, kind of like chaos network or whatever, where as you're training, so this is going back to training, you would actually snip 50% of the connections, let's say. That's a fairly common number. If you did 0 dropout, it would be the network. If you do 50% dropout, you're saying sort of randomly snip connections. And it'll take a second for this to sink in if you're not familiar with it, but really what you're doing is creating a new network each time that you're going through. And so this way you're sort of impeding that network's ability to pick up things it shouldn't be picking up. You're kind of forcing it to find the real data behind this, or the real model, like the real fit to this data. And this didn't really make sense to me much until I was talking to my Google Brain buddy, who went to OpenAI, and I think he's on his own now. He was explaining, so he worked on Street View. And specifically, he worked on training the model so that it would detect like addresses of people's faces and things like that. And so he would always talk about how they would feature engineer, or they would crop these, or not crop the images, but they would pre-process these images and blur out the like interesting parts that they wanted the network to learn. So they would blur the numbers out, they would blur people's faces out on purpose, because there was a bounding box that said, this was training data, or this is training data that had been labeled and said this is something that you shouldn't show. And by blurring it and changing the background, and like doing all kinds of stuff, you're sort of doing something similar to here, except you're doing it with the layer, or the like data. And you can actually go from, you could start to have 5 times the amount of data, 10 times the amount of data, the same data set, but you could start to kind of impede and then force the network. And so that then ends up with a more powerful network. And specifically, this is like an implementation detail of TensorFlow. When TensorFlow is doing this during training, the way that it compensates for it during when that model's been frozen and pushed out is it's boosting all the other ones. So we think of it as snipping, but actually TensorFlow is boosting all of the non-snipped connections. And then that way everything falls in, and it kind of makes the move to production probably much easier. Because otherwise you have to kind of maintain which ones were like held out. And so that's one of those subtle differences that is literally one line in the documentation. And it's like, to me, it's the most representative of how the like other sort of offline, cafe and things like that are doing it, or like we're doing it. And now a like production-focused machine learning AI platform that's doing things with train to serve in mind. Okay, here's the XLA stuff. High level here, since we only have 9 minutes, is XLA is both a training, so it's kind of think of it like an intermediate representation. Think of it like a logical query plan to a physical query plan, right? And what's happening here is we, the TensorFlow like developer or data scientist, are constructing these graphs of like operations that we're doing, and then but we want a way for hardware people like the Nvidia folks, like Google themselves for the TPUs, can plug in and grab the sort of optimized logical plan, or whatever you call it, and then convert it into a like optimized physical plan. It's not really a query, it's kind of but yeah, like you get the idea. And so there's a couple chip vendors that had started about 2 years ago, because these like turnaround cycles for hardware is about 2 to 3 years. And so they actually started off before XLA was getting more and more full featured. And then Google dropped XLA, like meaning they like released it, and then now these hardware vendors had to plug in to like XLA, and they're like, oh crap, we have to support this. Like they were each kind of doing their own. They would take a TensorFlow graph and yeah, actually the Nvidia folks are now starting to move over to this XLA, because right now TensorRT is literally looking at your raw graph and then like doing its own optimizations. And that will only go so far, because they're doing quite a bit at kind of the logical optimization plan area, and yeah, you want to inherit that. Some of you might be thinking LLVM, and not surprisingly, actually TensorFlow uses LLVM to get to the very, very last mile. Right? There's so much LLVM support. That's a layer that can go, it's got its own syntax, and they are doing all this XLA stuff to get it into LLVM, and then from that layer, then it goes down to the ARM, to the to NVPTX for the Nvidia. Yes, LLVM is a project out of Apple, actually. Let's see. Oh, so here's that chart. Or yeah, the comparison. So there's just-in-time compiling that's being done. So this is on training side, and this is a bunch of operations that, there are 16, 20 of these that required you to move memory from CPU to GPU. Every one of those was a candidate to start with the CPU, move memory over to the GPU. That GPU got bored or whatever and sent it back, and then the next operation comes in. On the right is that same cluster, but it's been fused together into one physical kernel, one C kernel that works on that GPU, operates on the data, huge batch of data once, and then moves it all back. And this is pretty much the closest thing if you've ever read about the Spark project Tungsten. It's doing this with the JVM instead of C. Here's a way to visualize it. Let's see. Oh, and so from this point on is all going to be inference for the next 5 minutes. And this is the same XLA framework, but now used in this TensorFlow Light sort of context. The old name of it was TF Compile. All right, yeah, so I was describing this before, where it starts at a node, goes to the predictions, and then the Halloween bucket. There's also something called the graph transform tool, and this is kind of a generic framework that can do the graph traversal and all the busy work, but then gives you a bunch of operators out of the box for quantizing from the floating point 32 down to int date, down to FP16, right? So again, this is all post-training from this point on. So yeah, before optimizing, so this is like an example of this transform graph. This actually is not part of the regular pip install. You actually have to compile TensorFlow from source to gain this. So after one pass through the graph transform tool, we actually go from the gobbledygook down to this. There's still a couple pesky sort of training side things that were left over because they were actually in the path of the input to the output, specifically those identity things. So we strip those out, make a few more adjustments. A little bit of quantization. And finally, we're now ready to actually freeze the graph. So now it's just 5 nodes. We've actually burned, so the term freeze is it's converting variables which want to be trained into constants. And there's huge gains in performance when you go from a variable that can have write operations and mutable characteristics into a constant. So it's a subtle difference, but it's a big one. Here's the multi-headed inference, right? So again, we're getting the human readable prediction, but then also getting that final layer to then pass it. I think that's probably it. I think the rest of it's like Kubernetes stuff. Any questions? Yeah?
Chris, I mean, this is next level. I'll admit that I'm confident about myself to say that I probably follow them. But I really am fascinated, and I want to know a lot more about the engineering side and optimization. And I know this wasn't specifically about your product that you guys built, but
yeah.
You guys have more ramp-up videos to novices on how to get started on using your package and integrating it with something you built yourself, all the videos online, something like Answers.
Yeah, so like we actually do like a monthly what's it called, community dev call or something that we call it. Those are all on there. If you go to pipeline.ai, there's a community tab, and all the videos and everything. It links to the Meetup videos and all that stuff. Yeah, they're all on YouTube. But yeah, there's tons. I'm not very good about editing the video, so it's 5 hours of me just babbling, typically in a lot of cases. So it's not very approachable or indexable from that standpoint. But if there's a particular aspect, I could try to point you to a couple of specific videos. Yeah.
You said the community edition of your product kind of just slot in already got something on I mean, how much do you have?
Yeah. So we're going for one of my kind of mandates when you're on Community Edition, which we actually haven't like released the latest version. I'm trying to think if I have a, I think I do have a dev version here. You could literally, so this is, you know, what's good, and yeah, so this is where you could actually upload a new model. You could even drag and drop a model or source code. It'll train it for you. It'll distribute it across the cluster. What we're going for is a Save As button up here. And it's saved, and so this is the new community edition, by the way. It just hasn't been released. This is a train button. I'm trying to get my buddy to not use that, but you would literally do Save As. So I saw this with Databricks because I was a field engineer for Databricks, and so it's not as easy as just Save As and give me your Amazon keys, right? It's like, you know, yeah. Yeah, so the sort of intermediate, we go back and forth on this literally every day. We talk about it because it does affect our designs and our priorities and all that. But even if we could do a Save As and spin up your own subdomain, right? And then, but then that's us bleeding into the managed service. And like we don't want to be a managed service, but we do. I mean, it's way easier to, you know, to manage a managed service than to manage like Cloudera, you know, 5,000 installations of pipeline everywhere. Yeah.
You have maybe a service that's 15 like that.
Yeah, and that would be like the Save As kind of thing. The people that we've been working with since the beginning are not people that would ever give us their models to serve or to train or do anything. Because one thing, these models, while they don't necessarily have protected information in them, they're like derived from sensitive data. And so depending on who you talk to, right, like literally this is one of our sort of intro like questions that we ask when we're talking to a new customer is, well, A, how close can we get to production? Can we push models out straight to production? And like 99%, the answer is no, fuck no. They're like, we're not going to give like any, you know, like data scientist or like anyone, DevOps person, you know, the ability to push out just kind of willy-nilly, right? And so like we have to show that these tools are just as fast as you can get it out there. You could also tear it down. It's in shadow mode by default, so you have to actively turn it on. You know, you can put workflows. But yeah, and then the second question is, do you consider your models as secure and private as the data it was trained on? And some people, I'd say 70% of the people are like, oh yeah, we probably should think of it that way. And then, because with Databricks, for example, people, how do I say this without sounding like a jackass? The kind of people that were willing to use Databricks and give us their data were kind of the enthusiast kind of thing. And you know, Databricks, when they're given $140 million, or I think almost $200 million now, has to target different type of user, right? So, what would you want to be doing though? Like for example, you know, you'd want to be able to train a model, push it out, get the rest endpoint, integrate it with your
pseudo production.
Yeah.
Something like how I would do it.
I see. Yeah, and it's funny because it's something I would want too, right? And so we have this internal conflict of, are we building what we want, or are we building what, you know, the VCs want kind of thing. Yeah, I think the reality, we're definitely going to have a Save As button, and it'll probably be, if you want to actually get this installed in your VPC, then follow these instructions, and that's a bit higher touch, right? With like Databricks, for example, they were all about zero touch. They wouldn't use the word no touch because no has a bad connotation. So it's weird shit like that, right? I mean, it's not a Databricks thing. It's more of like a DC thing and how you.
I mean, I love Databricks. I don't know what that means.
Yeah.
3-4 years ago.
Yeah.
I wouldn't say anything bad.
Yeah.
You know, things move on, and AWS get a lot stronger.
Yeah, these things. What's interesting about SageMaker is beyond using their models, you still have to provide a Docker image. And so that's why we were so excited when they finally released. And yeah, we actually have a quick start for SageMaker. So, because people are like, oh yeah, that's great, I can serve my own model, but holy shit, where do I start? I don't know how to create a Docker image. And that's exactly what, The weird thing is that we're not really making money on this part because it's the open source feeding into SageMaker. So in that sense, they're a competitor, but our story is, well, because you could actually use the exact same APIs on SageMaker, Google Cloud, and on your own Kubernetes cluster. So it's like the exact same tool. Same like REST API, same CLI. Yeah. Thanks for coming. Sure.
So my question was, you mentioned that with different versions of Python or different packaging, performance can be dramatically different. Then the expectation as a user would be that I will be packaging or duplicating those Docker images with Intel Python and with Panda Python.
Correct.
Runtime using your product and switch.
Exactly. Yeah. So from a UI perspective, which helps me kind of grok it and explain it, you would add the model, either drag or drop, the source, whatever. This button is really an optimize and deploy. So this button actually generates multiple versions, and when you click it. Right now we have chips exposed, and we have the runtimes here. And so this is just Python versus TensorFlow Serving versus TensorRT and Java. I think there's a couple more, but yeah, it would be so there'd be another one that would be Intel Python or something like that.
Related question on maybe so you also mentioned about support scikit-learn.
Yeah.
In that case, just a menu change
Absolutely, yeah. For scikit, it would be Python. And actually so this is a model that's already been uploaded. Here, we would say model type, if it's scikit. This is just one way to add it. Yeah, so here, you would say PyTorch, scikit, and then you can select CPU, TPU, GPU, whatever, and it'll, provide the model path, things like that. Either S3 bucket, GCS, all that. Yeah. And why you're doing this is you might want to be comparing a scikit version that you currently have to a TensorFlow version or a PyTorch version. What we saw, we've seen this more than once actually, is people use Keras and then they have the TensorFlow version, and it's some crazy recurrent neural net, and they build a Theano version. And actually, probably, I'd say 60% of the time, the Theano version for that particular model was faster. It was significantly faster than the TensorFlow version. Now, they just deprecated Theano, right? It's pretty much end of life or whatever. So those people that made that choice at the time are now scrambling to put it. Keras, you just change the backend theoretically, but they never would have known if they couldn't do something like this, right? And at that time, it was more of the online stuff. But one other thing I didn't focus on that is, of course, part of the open source stuff is the actual insight into the model. So I could show you just one quick dashboard. Specifically, so every prediction logically is three different. It's like transforming the input, which is JSON or CSV or something like that, and then providing, and then calling the prediction, and then transforming the output back into something that is good. So in the Kafka case, for example, Kafka Streams predictions, you would have Avro coming in, you would make a prediction, then you would put that prediction onto another Kafka topic as Avro. And so, but TensorFlow doesn't know anything about Avro, right? So you have to convert it into NumPy. And we actually have the Python libraries where you could just annotate or decorate within Python. You would put a decorator in there and say monitor this particular method, which could be the input transformer. And what we saw, if I can find it, it'll make more sense. We actually had a time where somebody pushed a change and it affected the overall prediction, but we couldn't explain it. Yeah, here it is. So just by, like, bare minimum to like participate in this pipeline stuff is you just need a predict method that takes a request as bytes and can return bytes. And then it's, super generic. And there's like already logging that comes with that. But this is only logging for the entire predict method. We can actually go one step further, and there's those 3 logical steps: transform from JSON into NumPy, make the prediction. It's a scikit model in this case, and then take the NumPy and convert it back into JSON. And they actually made a change to both the model and to the input transformer. And I think it was specifically converting CSV into NumPy. And at first they had built their own, and then they got fancy, or somebody suggested, hey, why don't you use the Pandas CSV? The code's cleaner. The problem is that Pandas is optimized for batch conversion, like batch CSV conversion, and not this sort of low latency stuff. So what had happened was they had made both changes, and we didn't have this, like that's actually where these libraries came from, where this level of insight came from. We were trying to make it easy so that the developer didn't actually have to do anything, which we're still doing for the bare minimum, but we wanted to put timings around specific parts. So once we did that, we just took like every line in there and just wrapped it. And so now instantly with that name that you give it, it then starts showing up in the same, this is for file Prometheus. And what had happened, so this is the normal case where the blue is the predict, and that's really where most of the time should be spent. What we saw was green, which is the request transformer, jumped up higher than predicted. And so that was a clear indicator that it's not the model that had brought that, it was the actual input transformer. And we then looked at the, we were so focused on the model part of it, and yeah, it was actually just normal code. But it was like, I think it was like 14 milliseconds up to like, I don't know, 75 milliseconds or something. And all the offline testing of that model didn't show any difference. But it was, yeah, and the same thing could happen on the response too. Because some of these requests, especially as a model, is people are trying to get more and more out of a model, they start passing in much broader data, and like, oh yeah, let's just add this feature and try it out, and then these input transforms become huge.
The creation of Docker images could be using CI/CD.
Exactly. Yeah. So we plug into Jenkins and all that. What was cool was I actually poached one of our the champion of one of our early customers from Expedia. So we were working really closely with them to make sure that we had all the enterprise hooks, and because we're very careful about because we've been on the other side of this stuff where we don't want people to come in with this huge framework and we don't know how to manage it, and we have no idea what's going on. So we're very careful about exposing all the logs and using FluentD and all the standard practices, and we hook into Datadog and all the they're normal metric stuff. So you can get basically everything out of the system that you need, but you don't have to worry about some of those details. But yeah, certainly, we have a Jenkins webhook that'll basically invoke it, right, and then tags it all the way through. We're seeing a lot of people using Artifactory, by the way, for everything, jar files to Docker images to models. Yeah, there were people I see this everywhere. People try to use GitHub large file thing, and that thing isn't, I don't know what's wrong with that service. It's not that good. And then they switch over to something like Artifactory.
One of the questions that I had was, in terms of tuning the model, I was thinking about maybe tuning the feature processing pipeline or tuning the machine learning hyperparameters. Is that supported with this?
Of course, yeah. So, in fact, we go one step further where we can show you hyperparameters at these 3 phases, right? The training phase, the optimization phase. Where is it? I have that one slide that has. Yeah, so these are, this is kind of the main dashboard to see the whole pipeline. And then here, so this is where you would actually instrument your scikit training pipeline, the end of your scikit training job and show what the actual learning rate was, and then down here is the actual observations. So validation, like accuracy, training accuracy, time to train. It's just a pipeline API call, and that goes into what we call PipelineDB. And then we can, so we can do like hyperparameter tuning basically on the entire pipeline and see things that happen offline, how do they affect online, which optimizations actually change anything, right?
You mentioned about PipelineDB.
Yeah, that's one of the things that we've, it's not yet feature complete, so that's not really answering the question, but it'll most likely be one of the holdout things, yeah, because it ties in, it's, in VC speak, it's the stickiness part of the product,
So then if I had this product, to message to the database?
Of course, right. That's actually a good idea in my community focus, is that, we're kind of leaning towards like the Cassandra type thing, which we're a bit, so like we all have Cassandra experience at Pipeline, but that's almost why we're not going to choose Cassandra, because we have so much Cassandra experience. But on the training side, it's very low volume because it's after a training job. If there's hundreds of training jobs, that's not a lot of traffic. On the prediction side, every 15 minutes or 5 minutes or whatever, we're actually updating. And if you have 1,000 model servers that are saying this is what our current like latency, 99% latency, that's a lot of traffic. And so, that's the part that, but you're saying, could I switch out the back end and still use those? It's not, it's kind of architected that way, just like natural separation of the layers. But it's not something easy to do. Yeah, so where do you work? Do you? Well done. Have I met you before, ever? Yeah, I was at IBM, and then IBM. Yeah, do you know Trevor back there from Chicago? Which team are you on with IBM? Yeah. It's all Watson these days, isn't it?
By the way, I stayed so long because I wanted to say hi, because I actually know you from the O'Reilly courses.
Oh, cool.
You might even vaguely remember me by my actions because I asked you about the pancake stack.
Oh God. Oh yeah, didn't I comment on that? That like of all things people remember me by, it's